A multi-master directory partition is a complex network environment where multiple servers can receive and process data updates simultaneously. Maintaining state consistency across this environment presents a strict architectural challenge. Data updates must propagate across the network instantly, but the system lacks a single master clock to sequence those events. If two distinct nodes update the exact same data entry at the exact same millisecond, the system requires a deterministic method to perfectly resolve the conflict. The system must execute this synchronization under strict bandwidth constraints. To prevent network saturation, redundant data can never be transmitted. Resolving this concurrency problem requires entirely decoupling local update sequence numbers from originating update sequence numbers. An update sequence number, or USN, is an internal incrementing counter maintained by a specific server to track changes. By separating the local USN from the originating USN, the system generates the metadata required to operate two specific mathematical sieves, high-watermarks and up-to-dateness vectors. Achieving near-zero replication latency while minimizing bandwidth relies on a single principle, isolating where an update happened from when a local server learned about it. To understand how this isolation works, we start with a simplified baseline: two domain controllers, DC1 and DC2, in an empty network. A domain controller is a server that responds to security authentication requests within a computer network. This split-screen data table tracks the creation of a new user object on DC1. Upon creation, DC1's local USN counter increments from 4710 to 4711. It assigns that 4711 value to the object's originating USN. Because this object is brand new and has not yet been modified, its USN changed attribute perfectly matches its USN created attribute at 4711. We then trigger the replication of this new user object from DC1 to its direct partner, DC2. The data packet transfers specific metadata, the originating USN of 4711, and a version stamp that records the exact originating time and DC1's identity. While DC2 imports the originating metadata, it relies on its own independent counter for local processing. DC2 assigns entirely unique local USN and USN changed values, such as 1746, to the object. From the moment of creation, every attribute carries a dual identity: local metadata proving when a specific server processed the data, and originating metadata proving where the data was born. Looking at the DC2 table, an update event occurs. A user changes their user password directly on DC2. Because of this local update, DC2's local USN counter increments sharply from 1746 to 2453. Because the change originated on DC2, the password attribute's originating USN is overwritten to match DC2's new local USN. The update also generates a new version stamp. The version number increments by exactly 1, establishing definitive priority over the previous password. The system now initiates the replication of this password change back to the original server, DC1. Upon receiving the update, DC1 increments its local USN changed value to 5040 to reflect the processing time. However, it strictly imports the version 2 stamp and the originating USN of 2453 from DC2. By pairing a static originating USN with an incrementing version stamp, direct partners blindly accept the most recent updates without risking infinite replication loops. This diagram maps out a multi-node network, scaling the scenario up from two direct partners to a sprawling mesh of domain controllers that replicate transitively. In this expanded model, a redundancy problem emerges. Node A updates an object and replicates it to Node B. Node B then transitively replicates that same object to Node C. When Node C subsequently requests a routine update cycle directly from Node A attempts to send the exact same object that C already received from B. Destination controllers require a mechanism to preemptively inform a source exactly which changes they have already received from the wider network. The system resolves this using replication request filtering, which leverages the USN metadata previously established to block unnecessary data transfers. Without request filtering, a multi-master network generates exponential redundant disk I/O and CPU processing, eventually collapsing under its own weight. The first coarse layer of replication filtering is the high-watermark, also known as the direct up-to-dateness vector. This is a value maintained by the destination controller. In this diagram isolating two nodes, the high-watermark represents the highest USN changed value the destination has successfully received from one specific source partner. At the start of a replication cycle, the destination sends its high-watermark value to the source. The source controller filters its internal database by presenting changes strictly in increasing order of USN changed. If an object's USN changed value is less than or equal to the destination's high-watermark, the source completely skips that object. The high-watermark acts as a coarse sieve. Dropping irrelevant objects entirely before they are packaged drastically decreases CPU compute time and disk reads. The high watermark has a strict limitation. It only filters based on direct relationships. It ignores updates received indirectly via transitive partners. This table inside the destination node defines the up-to-dateness vector, an array tracking the highest originating updates received from all source controllers. It logs the database GUID, a globally unique identifier assigned to each server, paired with its highest originating USN. When requesting changes, the destination provides this entire vector table to the source controller. The source applies a secondary filtering logic, cross-referencing the destination's vector table against individual attribute USNs within a specific object. If the destination's vector guarantees it holds an equal or higher originating USN, the source strips that specific attribute out. The up-to-dateness vector acts as a fine sieve, eliminating specific, redundant attribute updates that arrived via complex, indirect network paths. Administrators use the metadata generated by these vector tables for network diagnostics, leveraging a feature introduced in Windows Server 2003. The system records a timestamp on the up-to-dateness vector every time a full replication cycle completes. This occurs regardless of whether actual data changes were received. Examining these vector timestamps automatically identifies inactive nodes, triggering an Event ID 1864 warning, a specific error code in the directory service, to alert administrators. The system relies on a dual filter architecture. High watermarks prevent irrelevant objects from being processed locally, while up-to-dateness vectors filter irrelevant attributes globally. The speed and reliability of a massive distributed directory is entirely dependent on the mathematical isolation of local state changes from originating state changes.